This video will close out our lecture set on hierarchical linear modeling by running some hierarchical linear models using SPSS. To demonstrate this, I'm going to be using a data set for HSB, stands for high school and beyond, regarding some characteristics of students nested within different schools. In my data set, I have several variables. I have an ID variable, a minority variable for students, uh, sex variables for students, socioeconomic status, and math achievement, which is going to eventually be my outcome. I should note that this ID variable, you'll note, repeats for rows 1, 2, 3, 4, and 5, and that's because the ID represents the school. So this is the school ID rather than the student ID. On the right-hand side, I have some characteristics regarding the school as well that we'll play around with when the time comes. This may be a long video. There's a lot to demonstrate here, so we'll see how far we get, and then maybe we have this broken out into 2 videos. It'll kind of depend. All right, so let's go on and get started. To run a hierarchical linear model in SPSS, I go to Analyze and then Mixed Models. Recall that mixed models is another name for hierarchical linear modeling. I'm going to select the linear option, and this pulls up my menu where I'm able to identify whether I'm doing subjects nested within a particular variable or repeated measurements nested within a particular variable. In this particular case, I have subjects nested within the school ID. So I'm going to move the school, that is the second level variable, over under subjects and click continue. Now I can enter in my model for whatever model I'm going to fit first. In this particular case, what I'm going to focus on is the intercepts only model. As a reminder, the intercepts only model just looks at the intercept. So I have y as my level 1 equal just the intercept plus the random error. And then in level 2, the intercept is modeled by a fixed component for intercept plus the random component for intercept, which allows schools to have different math achievement scores. Combined, again, I see fixed component, that is the overall intercept, plus school contribution or level 2 contribution, plus the random error at the student level. So this model is asking, is math achievement, I have an overall average math achievement, and then I have school component variability for math achievement, and we can test if that's related or not. To fit this, I'm going to move math achievement to be my dependent variable. I'll move to the fixed menu and make sure that include intercept is checked to allow the fixed intercept term. I'll move to the random menu and make sure that include intercept is checked to include the random intercept term. And I'll also go ahead and move ID from subjects to combinations, further indicating in SPSS that I should group subjects based on ID. There's not much to do in estimation, as I'll use SPSS default of REML instead of ML, that is reduced maximum likelihood instead of maximum likelihood. But in this particular case, you could click on it and see where you can see the restricted maximum likelihood term, maximum likelihood, and then you can make that selection. Under statistics, I'm going to check 3 boxes, the parameter estimates for fixed effects, and test for covariance parameters and covariances of random effects. Go on and click OK. I'm going to ignore these last 3 boxes and simply hit OK to run this intercepts only model. Now what I can see here for intercepts only, I scroll down a bit and I see the 2 tables that I end up interpreting, the fixed effects table and the test of covariance parameters. I only had an intercept, so this is an intercept only regression model. That's my only fixed effect. And we typically don't interpret significance test of the intercept, doesn't really matter. It's just saying that average math achievement was different than 0, which is probably good, I guess. Guess it depends on what 0 means in math achievement. Here we have estimates of covariance parameters, and this is a little bit more interesting. In my residual, this is my standard error term. The intercept is the new one, subject equals ID. That is, my individuals are nested within my ID groups. So we're asking, is the school level variability in math achievement statistically significant? That is, or does it vary from school to school? Does school matter? And here we find that yes, school does matter. There is a statistically significant effect of school level math achievement with p less than 0.001. One other thing that can be handy to calculate in this particular case is the interclass correlation coefficient. And to do this, I'm going to go on and copy this table over into a Word document and then go through the calculation. So in my Word document, I have my different covariance parameters, and I also have my interclass correlation coefficient equation. I take the variance from the random component of the intercept and divide by the sum of the variance from the random component of the intercept plus the variance of the random error, or in this table, it's called residual. Now, these components are located in the estimate column in my output. So for the random intercept, I'll be taking this estimate column. That's the variance of the random intercept component. That is the random school effect. And then for the error, I'll be taking the variance component of this. I'll go on and copy and paste these values into my equation. So I end up with, again, the variance in math achievement due to school divided by the variance in math achievement due to school plus the variance in math achievement of students above and beyond the variance attributed to school. Now I can pull up a calculator and quickly calculate this. I'm going to type in 8.61 4025 plus 39.148322. That's going to be my denominator of 47.762347. And then once I have that denominator, that's everything on the bottom, I'm going to take everything on the top. That is, if I can clear this out, 8.614025 and divide by everything from the bottom, that 47.762347. I end up with 0.18. That is, about 18% of the variability in math achievement is due to the school level effect. Now, if this is high or low really depends on the field that you're in. I can say, however, looking at my table, that this effect is statistically significant. And within the concept or context of education, 18% of variability in student scores explained is pretty meaningful. So I'm going to be using a level 2 model, and this would be my justification for why I'm using a hierarchical model, is because the statistical significance of the level 2 term is statistically significant. And at a more practical level, 18% of the variance explained in math achievement is, from my perspective, something worth accounting for. That is, I'd rather account for that extra 18% than not include this component of the model and not account for that extra 18%. All right, let's go on and close our output and fit another model. Now that we've determined that we're going to be using this hierarchical linear modeling, one good basic starting place could be to include a random intercept to allow each of the schools to change based on math achievement. In this particular case, what I'll be looking at is probably the effect of socioeconomic status on math achievement. And then we'll account for the clustering effect by allowing school to affect math achievement as well. The model's going to look like this, my random intercepts, where X represents socioeconomic status, Y represents math achievement. Note that my intercept is allowed to be random. That is, for my intercept term, I'm allowing the schools to have different average math achievement effects. My slope term does not have a random component. That is, I'm assuming the impact of socioeconomic status on math achievement is consistent or constant among schools, and we can change that later. So I'm still going to go to Analyze, Mixed Models, and Linear to fit my random intercepts. I'm going to leave subjects as ID as before, but now I'll move socioeconomic status to the covariate list. I need to be quite frank with you. I really detest how SPSS handles quote unquote factors versus covariates. I highly recommend not at all using this factors, but instead dropping all of your variables into covariates. Even for categorical variables, which I would normally include as factors, the way that SPSS incorporates this is, from my perspective, buggy. What I would do is I would make sure that all of my categorical variables that I would want to include are dummy coded and include them as covariates instead to allow for the correct and accurate parameter estimates. After I've included SES, it seems like in SPSS, this should be listed as a fixed effect, but it's not by default. So I have to go into SPSS and tell it to include that fixed effect of socioeconomic status. I'm going to go into random effect, make sure the intercept is included, but note I'm not allowing the slope of SES to be random. So I'm not going to play with that at all. And I'm not really going to change any of my other options. The only thing that I've done is added an X variable to my last model. So this requires pretty minimal updating. Going to click OK and scroll on down to see the results. I have two terms. I have my regular regression coefficients, I guess you could say, and my covariance parameters, that is the effects of the level 2 model, the school level changes in math achievement. In this case, I can say socioeconomic status is positively related with math achievement. That's a statistically significant effect, and it's actually a rather large statistically significant effect depending on the scales of these variables. And this is after accounting for the clustered nature of the data. That is, after accounting for the fact that students are clustered within schools through allowing school average math achievement scores to be different. Down here, I can test still if the math achievement scores differ by school, and I can see, yes, there's still a statistically significant difference between math achievement and among schools. Schools have different math achievement scores. That is, including this random intercept is an important component. All right, well, what if I wanted to continue my exploration of this model through adding a random slopes term? Well, adding a random slopes term is absolutely possible. We simply add this u sub 1j to our equation. And that's really all it is in the equation. Everything is the exact same except for u sub 1j. And what this is going to do is, in addition to allowing each school to have their own math achievement scores, this is going to have each school have their own relationship between socioeconomic status and math achievement. That is, perhaps some schools, socioeconomic status is a bigger impactor on math achievement, and perhaps at some schools, socioeconomic status doesn't have a particularly large impact on math achievement, and we're going to test if that's true or not. To fit this model in SPSS, I'm going to go on and X out of my old output, click Analyze, Mixed Models, and Linear. I'll keep ID under Subjects. I'll keep Math Achievement and the covariate as Socioeconomic Status. Under my Fixed, I'm not adding any fixed terms. Socioeconomic status stays a fixed term, But now I'm letting the coefficient of socioeconomic status be random. So I need to move SES into the random effects model. Now it's important, very important to know that when I move socioeconomic status to be a random effect, I now have two random effects in the model. In SPSS, this requires an additional step, and it only requires this additional step when I add a random slope to a random intercepts model, or have two random components or more, then this extra step is required, and that is to change the covariance type. The default covariance type is called variance components in SPSS, but when I want to have two random components, in this case one random component for the intercept, allowing schools to differ on math achievement intercept, and a random component to the slope, allowing schools to have different impacts of socioeconomic status on math achievement, then I need to change this from variance components to unstructured. After this is changed, I'll click on Continue and then click OK to run the analysis. Scrolling down, I see my estimates of fixed effects, and I haven't added any fixed effects, so nothing here is going to change, save maybe that the parameter estimate might be impacted now that I'm allowing the parameter estimate to be based on different schools. In my estimates of covariance, I can see that there has been a large change in that I've added two new rows, UN with 2,1 and UN with 2,2, in addition to my original intercept role. How I interpret these is as the 1,1, UN stands for unstructured. This refers to the covariance change that we just did. 1,1 represents the intercept, that is the first random effects term, the intercept in our model. It is still statistically significant, indicating that math achievement is statistically significantly different depending on which school you are on average when socioeconomic status is 0. And socioeconomic status in this example has already been standardized. So that means if you're at the average socioeconomic status. So at the average socioeconomic status, the impact of school on math achievement is statistically significant. Or schools are statistically significantly different than one another in math achievement. I'll skip the middle one for now and go to this second component, 2,2, which represents the random effect of school on the relationship between socioeconomic status and math achievement. That is, do different schools deal or have a different relationship between socioeconomic status and math achievement? Incidentally, if this were true, we might look at schools that have a lower relationship between socioeconomic status and math achievement, because these are schools where it doesn't matter your family's wealth, everybody's doing relatively equally, which might be a good thing. Of course, it might be a bad thing. Everybody could just be sucking, but might be a good thing. In this particular case, I can see that this is close, but not completely statistically significant. Now, I will say, and this is noted in your textbook, in SPSS, this is constructed as a two-tailed test by default, and we divide the p-value by 2 to interpret it in the correct direction. So even though this looks like it's not statistically significant, this actually would be interpreted as statistically significant, as 0.79 divided by 2 is 0.03, 0.0395? Which is lower than our traditional cutoff of 0.05. So this would be interpreted as statistically significant. Really, either way, I would consider this to be a marginal factor. So this could be an influencer, but I'm not convinced by the amount of evidence here. This is borderline. So schools may vary somewhat on this, but it doesn't seem to be a large contributor. And whether or not it's statistically significant, and again, we would interpret this by dividing it by 2 and comparing it to our traditional cutoff in SPSS. It's a very SPSS unique thing. I was going to call it a feature, but it's not. It's a flaw. It's a very SPSS unique flaw. So for this, again, we would probably interpret it as statistically significant, but I'd interpret it with a bit of caution in that the effect is not particularly pronounced, and we have a moderate amount of evidence that this isn't just a random thing, but not a particularly convincing amount of evidence. That is, I would keep an eye on this if using this and interpreting it, the schools to have different socioeconomic status effects on math achievement. I might keep an eye on that particular effect if I'm making a conclusion in that direction. All right, for this middle one, this middle component represents the relationship between the random effect of school on math achievement and the impact of school on the relationship between socioeconomic status and average math achievement in the school. And in this particular case, we can see there is no statistically significant relationship there. That is, as the school has a better math achievement or a worse math achievement, there doesn't appear to be a relationship between the average math achievement of a school, that random effect, and the relationship between socioeconomic status and math achievement at that school, that additional random effect. So those don't appear to be statistically significantly related. Again, our fixed effect, socioeconomic status, is interpreted in light of the random effects having been constructed. Same thing with the random effects interpreted in light of the fixed effect. So in this particular case, what we're saying is socioeconomic status is a statistically significant factor after accounting for the clustering of the data in the school's impact on math achievement and the school's impact on the relationship between socioeconomic status and math achievement. On this video, we've discussed how to fit several basic models in hierarchical linear modeling using SPSS.